on this set. It's going to be for slightly different reasons, though, right? Like, well, I guess that's the question. Is it actually true that it's equal to there? I'm not so sure it's actually true now, because what is log alpha? What is log alpha of x? Well, it's natural log of x, right? Plus I arg alpha. So, in fact, we don't get agreement of the principal logarithm and the log alpha logarithm on the real axis for any choice of alpha. Like, it has to be the case that this is 0. Only in that case would we get agreement and an expectation that, and then of course we'd only expect that they match on the intersection of the domains of the, like, you started to see all of these things in that homework problem I gave you where you had different overlaps above and below the real axis. Like, we have to face all that. That's the music that we're up against here. So it's a subtle thing how this plays out for examples which have branch cuts. Okay, and then the other thing, to like completely understand this issue, you have to understand something called analytic continuation. So analytic continuation is, what it is like starting with a power series, right? Let me draw a picture of analytic continuation. So listen, there's all kinds of examples in this chapter that I should like talk about for you guys, because I know you're, a little bit loose on calculus too. So like there's tons of examples in my notes which are not in Gamelin that exhibit series calculation. Like you can multiply series using the Cauchy product. You can divide series like polynomials, long division, that generalizes to series. So I should show you guys some of those things, obviously. But I wanted to try to complete the story of the convergence and how this all goes through today. So analytic continuation is it's a subtle concept. So let me see here if I can. The definition is given here. We say f is analytically continuable. This is definition 5.85. F is analytically continuable. That's a mouthful. Anyway, I'm misspelling that. Along gamma, if for each t there exists convergent power series f sub t of z equal to the sum n equals 0 to infinity of a n of t z minus gamma of t to the n power for modulus of z minus gamma t less than r of t, such that Fa is power series representing f of z at z naught, and such that fs of z is equal to ft of z for all z in intersection of disks of convergence at s and t respective. Let me stop writing and just draw a picture. The picture is missing in my notes, which is unfortunate. Like, this picture really helps you. So the idea of analytic continuation is you start with a function defined maybe here at z naught, right? And that function has some initial disk of convergence. Let's say it's like this, yeah? Here's the initial disk of convergence, right? And then you've got some curve, gamma, like that, right? Then the thing is, it's analytically continuable if at each point along this curve gamma, right, you can find power series like here, for example, right? And there's a power series that represents it, and its radius of convergence might look like that. Maybe this is, here's my R of t, here's gamma of t, right? And then there's another one over here at S. And maybe it's bigger over here, I don't know. And then the point is that on the overlap of the, let me do it over here more. Let me do another one over here. So maybe over here you've got this. Here's, gamma of T2. And perhaps that overlaps with here's gamma of S2, yeah. And so here's the overlap of those disks. See that? Well, the point is that the power series representation at gamma of T2 and the power series representation at gamma of S2, they have to agree at the overlap. All right? Which isn't to say that they have to agree at everywhere. So, for example, what you could do with this idea is you could go back to our logarithm, right? And see what you could do is you could start with a power series for the logarithm centered at, say, 1, right? And then you could, in principle, you could follow the path like this, right? And so following that path, you'd have, I'm going to draw the circles of convergence smaller than they actually are for the sake of concept, just because it's, so like that, and that, and that, and that. And see, the analytic continuation of the function can go past branches, even though the original function can't. See, because the analytic continuation of the function is not the function anymore. It's something else. Yeah. And so you see there's tremendous potential for confusion here if you have it in your mind that the analytic continuation of a function is the same as the function. See, it's not. Right? Well, it doesn't have to be. It could be. It depends on the details. And so to properly understand this, people invented something called sheaf cohomology. Or sheafs anyway. Maybe not the cohomology so much, but there's something called a sheaf that deals with this kind of problem carefully. Because you need something more than just functions to understand it. And I'm not an expert in this stuff. It's I'd like to learn more about these things, but this is kind of as far as the course gets because this is very much beyond our pay grade to continue this discussion. But I don't even have a very good example of analytic continuation in the notes. But you can start to get a sense of it because of the way the logarithms, you can probably guess that when you analytically continue the logarithm, what you're going to get is the other branches of the logarithm, And so the idea of a Riemann surface is to kind of give these things a home. So you just, instead of having just the complex plane, the logarithm's Riemann surface is something like a ramp that just kind of continues up and around. And that way you can sew together the analytic continuations into a sheet, something like that. This is a topic for graduate complex analysis. So anyway, I think I gave you back your 9 minutes.
Yeah, it's 12:30.
Oh no! Oh no! It's 12:30. Yowzers. All my students are going to leave algebra if I don't get there right away. So I will try to make a video with the rest of the calculations that I have glossed over here just to try to settle chapter 5 for you guys. But so hopefully I'll get that done soon. But anyway, have a good break.